How do I encode RSA message? We simply compute the plain text M as M equals CD mod N to decrypt a ciphertext C using an RSA public key. Because both RSA encryption and decryption required modular exponentation, we should utilize the repeated squares algorithm if we want to make this operation as efficient as possible. These are the steps in RSA algorithm. So the first one is choose two large prime numbers P and Q. Calculate N, P, Q, and Z equal to P1, Q1. Choose number E where 1 easy. Calculate D equals E1 mod P1, Q1. You can bundle the private key pair as ND. You can bundle the public key pair as NE. As you can see, this is the RSA algorithm example. You only need to choose P, compute, choose E such that 1, compare a value for D such that public key, private key, the encryption of M, and the decryption of C. What is elliptic curve cryptography? Elliptic curve cryptography, or ECC, is a strong technique to encryption that differs from the well-known RSA method. It is a method of public key encryption that employs the mathematics of elliptic curves to generate security between key pairs. Due to its potential to provide same level of security as a RSA with considerable smaller key size, ECC has quietly gained favor in recent years. So how does elliptic curve cryptography work? An elliptic curve can be presented simplified as a set of points described by the equation y2 equals x3 plus ax equals b. The shape of the curve will be determined by the value given to a and b. Elliptical curve cryptography employs these curves over finite fields to generate a secret that can be only unlocked by the owner of the private key. The greater the key, the larger the curve, and the more difficult is it to answer the problem. An elliptic curve is drawn using the values assigned to points A and B. A line can be drawn across this place until it reaches point C, which is the third junction point on the curve. When the line reaches its third intersect point, we can reflect that point on the opposite side of the x-axis and this point. We can then draw a line from point to point C that intersect with another segment of the curve, point D, if we continue from point C. These points also reflected on the other side of the x-axis, and the process repeats until endpoint is reached. Each point intersection is presented by a dot. The intersection points in the example below will be described as follows. As you can see, A dot A equal B, A dot B equals C, A dot C equal D, A dot D equal E. Without the private key, the number intersection point is known, making very possible replicate the number times the equation was dotted.